Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Please raise your hand if you do not get a red mark. Is everybody good? Okay, so let's go ahead and apply our derivative rules. First, we can calculate, right? We can calculate the derivative of a given function by deciding what the overall rule is, right? And then applying our chain rule as needed. All right, so overall, we'll go ahead and plow in with our derivative of inverse cosine. The good news is we memorized our words, so it's going to be easy cheesy. I know the derivative of inverse cosine is opposite of 1 over the square root of 1 minus input squared, and then times the derivative of my input. Just my input in this case is in plain Jane x, it's e to the x itself a function. So I'll apply the chain rule times the derivative of my input. That would be times the derivative of e to the x, which is just e to the x. So it looks to me like fully simplified. We could make that a little prettier. We could say what? Negative e to the x over square root of 1 minus e to the 2x maybe? And we probably put that negative out front of the fraction bar. I just put it here because I was worried about making it fit on the slide. Raise your hand if you got the equivalent for number 1. The equivalent for number 1? Easy! Good job. Let's go ahead and take a look at number 2. If h is given by an inverse tangent, ooh, that's one of my favorite rules, I should say. So the derivative of inverse tangent is 1 over 1 plus the input squared times the derivative of the input. So for us, that's 1 over 1 plus input squared. My input in this case is x over 4 times the derivative of the input. Well, the derivative of x over 4 is just 1/4. And so if I wanted to make this a little bit prettier, we could go ahead and have this as maybe 1 over, and then you could do 4 all the way through. You could square that. Maybe I'll square that. So we'll do 4 plus, and then x over 4 quantity squared would be what? X squared over 16 times 4 would be x squared over 4. Is that right? What's that? About? Más o menos? Lo que sea? All right. Raise your hand if you had the equivalent for that. Great, and then this might not show up if it were multiple choice. I have to tell you that those multiple choice test writers oftentimes frown on including a compound fraction in the answer. So they might go ahead and make a common denominator and rewrite and simplify this. And so even though you did the calculus right, you don't want to miss out on easy points just because you didn't have the equivalent algebraic form. So how could we rewrite that one final time? Well, we could go ahead and create a common denominator. That would be 16 over 4 plus x squared all over 4, and then kick it up on top. So I'm just going to go ahead and say, I bet you that we had something like this. And I bet we get that for our final answer. Do you see what I'm saying? Awesome. Great. I'll box that bad boy, and then we'll do one more derivative calculation before an application to tangent line. If p is given by the natural log of square root of x, then p prime will be given by, oh, I know the derivative of natural log is 1 over the function times the derivative of the function. So for us, that would be 1 over the square root of x, and then times the square root of x. I know from time and time again, differentiating the square root of x, that it ends up being 1 over 2 square root of x. And so we can simplify this so long as we make sure that we can keep any original domain restrictions that the beginning function had. So this input was restricted to only non-negative x's, but a natural log function in general is restricted to only positive inputs. And so for us, it looks to me like I'm going to write 1 over 2x, but technically we should include the domain restriction x, right? Should be strictly positive because of my original. All right, we were practicing applying the rules, and so that isn't a big deal. But now in BC, right, as we move towards more complicated applications, we want to kind of be on the lookout for stuff like that, more so than an AB. Questions about the first 3? Can we do an application? Yes? Good. So let's algebraically find an equation of the line tangent to f at a given x value. So we did this a lot in AB. I know I need the same 3 things. I need my x coordinate and point of tangency, the y coordinate of the point of tangency, and the slope of the tangent line. The good news is that we get one for free. And the second's easily gained. So I can get the y-coordinate point of tangency by evaluating my original at my x value. Concern cosine 2 pi over 3 is negative 1/2. Is that right? Negative 1/2? All right. So I'm 2 out of 3, and the slope of the tangent line is gained by doing my y-coordinate. So go ahead and share with the class my first derivative, f prime of x, when I call on you. So what would my first derivative look like, Vivian?
Negative sine of x.
Awesome. And if we want to know f prime of 2 pi over 3, the slope of the curve at x equals 2 pi over 3, that's a simple evaluation. We'll simply plug in my 2 pi over 3 into my derivative function and evaluate. So it looks like the slope of our tangent line then is given by opposite of sine of 2 pi over 3. And so here we are, and we're at root 3 over 2. So negative root 3 over 2. Is that what you guys are getting? Negative root 3 over 2. Awesome. So I've got the x coordinate point of tangency, the y coordinate point of tangency, and now the slope of the tangent line. I don't know how pretty we'll be able to make this look algebraically, but it doesn't matter. All we need to do is solve for y to enter in our grapher and compare as it touches the curve. Then we can ask our calculator to draw a tangent and see if it traces over. So let's go ahead and write my final. We know what y minus y sub 1 is equal to m times quantity x minus x sub 1. So we know y minus my y coordinate of the point of tangency, that's negative 1/2, equals m, the slope of the tangent line was negative root 3 over 2, times quantity x minus, and the x coordinate of the point of tangency was 2 pi over 3. Do we get everything? Do we get it all? So that'll be plus 1/2, so I'm going to go gadget around, and I'm not going to mess around with distributing, right? Trying to combine like terms that aren't going to look nice with the radicals anyhow. All I'm going to do is take this plus 1/2 and subtract it over and enter my graph for 1. So I'm going to leave this as negative root 3 over 2 times quantity x minus 2 pi over 3. And then that would be minus the negative 1/2 would be y plus 1/2. Subtracting over would be minus 1/2 after the fact. Recall that this is exactly the form for our linearization, L of x, when we're using differentials to make approximations of function values close to a point of concern, x equals a. And so I'm just going to leave it like this because it'll be easy to check on our calculator. So raise your hand if you had this. Did you get this for your equation? And you might have made it look differently, but a quick check graphically should verify. So I'm going to go ahead and check graphically on my grapher. I'm going to make sure I'm in radian mode. Okay, and I don't know if that's going to be good, so I'm going to resume trig might be good. And I don't know what I have in there. Maybe squeeze theorem. From AB. Oh, here comes sine of x over x, and here comes secant of x. Forcing that red sine of x right there to have a limit that's equal to the limit as x approaches 0 of cosine of x and the limit as x approaches 0 of secant x. That's pretty sweet. All right, and a cool picture. In fact, I might want to take a screenshot just for Grace and Brendan and Tyler since they're gone. Okay. All right, so what do we need? Well, we need to clear all that in and out. And we need our original, cosine of x. And we need our supposed tangent line, negative root 3, close radical, over 2, open prime, x minus, oh boy, I'm going to try it, 2 pi over 3, close, and then minus 1/2. So right now I'm thinking that could be, right, that could be bad news bears. But if I zoom trig, and we're looking at 2 pi over 3, so 2 pi over 3 where should that be? Around there? Oh, look at that. Well, that's pretty good, yes, but I can't really tell from here. So what I'm going to do is I'm going to ask the calculator to draw tangent and see if it overtraces this line with a different line style. Yes? So while we're at it, that's for you, Grace. And now we're going to second program draw. Get it as close as recording. And we want tangent. And this is for you, Tyler. And my x-coordinate of concern then would be 2 pi over 3. Voila. And Brendan. Ah! Look at that, right over top. So my draw tangent command in blue overwrote our red that we had entered, and so that way I didn't have to mess around with the decimal. I didn't have to go in a separate step and go to my home screen and enter negative root 3 over 2, x distribute, combine lecture, and all that stuff, and see if these decimals are the same. So I kind of like that. That's pretty sweet. All right, we're not going to keep that. I know. All right, I do like this stuff. Okay, what questions do you guys have about today's Bellwork? Awesome. Then I'll go ahead and pause the recording right now. We'll take care of our OTL number 1. And the answer key was posted online for this, so it's off from there. Okay, ladies and gentlemen, so today's a quick whirlwind because we want to make sure that you guys are ready to rock and roll with your rules quiz. Again, 2 parts, first symbolic, and then stating the rules in words, so the verbal representation. And so now it's a special time for us. No, it's not Emily's birthday again, although that would be cool. It is actually mental derivative time. So we've got guest appearance, and we're going to go ahead and practice with this stuff. Awesome, and so we're going to go ahead and practice with mixed in rules for words as well. If you want to have your rules sheet out, symbolically you may. If you want to have your words out, symbolically, verbally, on your desk, you may, because we're going to do it right now. Get ready. So the derivative of a power function in words, math, PRB, rand int, 1 through 12, get ready. Yeah, in words, Sydney, get ready. Oh, not you, it's not you. I'm just telling you to be ready because it's going to call on you. I'm feeling a big 10 right now. Ready?
I'm number 9.
Number 5.
Function is the exponent times the base raised to the exponent 1 minus the exponent times the derivative.
Yes. Raised to the exponent minus 1, right? Times the root of the base. Excellent work. Excellent work. Next. That's x to the negative 1 right now. Everybody see it? Number 12.
3 over x squared.
So he says, you are correct. Good job. Plus 10. Next. Number 9.
4 secant 4x times tangent 4x.
So he says, you are correct. Good job. Plus 10. Oh, good.
Ready?
The derivative of a product of 2 functions in words is, get ready. Derivative of a product.
Hang on.
Number 2.
The derivative of the first times the second plus the first times the derivative of the second.
Nice work. Very nice. Plus 10. Number 3.
Negative 3x squared sine of x cubed.
Oh, you're correct. Plus 10. Bam. Derivative of, get ready. Number 4.
Oh,
that you?
oh my gosh. Okay. 4, negative 4. Wait. Negative, no, 4 cosine to the 3/3 times negative 4 sine x.
So he says, Yes, -4. There's my cosine cubed, and then times the sine and the negative came from the derivative of cosine. Nice work. Plus 10. The derivative of a quotient of two functions in words. Get ready. Number 7.
Derivative of the numerator times the denominator combined as the numerator times the derivative of the denominator all over the denominator squared.
Yes! I just want to write the word bottom, but that was very nice. Plus 10. Good job, good job. Derivative with respect to x of e to the 5th. Number 11? Skip
Can I
it. Number 2?
0.
Yeah, you're correct. Plus 10. The derivative of a trigonometric function in words is number 4.
The derivative of the trig function with the angle times the derivative of the angle.
Nice job. Plus 10. Very nice. The derivative of repeat. Number 10.
Cosine x or sine?
Hey, you're fast. Cosine x over sine x. Nice job. Way to go. Plus 10. The derivative of an exponential function is, in words, number 12.
The exponential itself times the natural log of the base times the derivative of the exponent.
So it says you're correct. I think got all the pieces. It doesn't matter for multiplication which order those are in. Nice job. Plus 10.
Puzzle.
The derivative of 7 to the negative x is number 7.
Negative ln of 7 times 7 raised to negative x.
Oh my gosh, you're giving me fully simplified stuff on the back. Can you like see through the screen, Shane? That's impressive. You don't have to give me the fully simplified version, but if you can, that's cool too. The derivative of an inverse sine function is, in words, inverse sine. Number 9.
1 over the square root of 1 minus the input squared times the derivative of the input.
Yeah, you're correct. I was too fast. Good job. Pleasant. Number 1. Number 8.
E to the tangent x times secant squared x.
So he says, you are correct. Got absolute power. Yes. The derivative of inverse cosine is number 6. Skipping. Playing college. Number 11. Skipping. Number 6 again. Skipping. Number 11 again. Whack, yo! Number 9.
The opposite of 1 over the square root
Not cool
of
stuff.
what?
Keep going.
The opposite of 1 over the square root of 1 minus the input squared times the derivative of the input.
Correct. Plus 10. You racked up the points. Oh my gosh.
So I'm winning.
Oh. So number 1. Number 5.
Negative, or -3 times natural log of 5 times 5 to the negative x.
You're correct. Good job. Very nice. Well done. Derivative inverse tangent is number 2.
1 over 1 plus the input squared times the derivative of the input.
Gosh, I'm not serious. Nice job. Plus 10. Number 12.
0.
You're correct. Plus 10. Derivative of natural log of a function. My other almost favorite one. Number 7.
1 over 1 times the derivative of the function.
Very nice. Plus 10. Ooh. Ah. Oh, popping fresh stove. Can we do that? You don't have to be fully simplified, but I bet you can. I can do the words. Ready, go. Number 10.
Oh, that's me. E to the x plus x e to the x.
Nice.
Nice. That's 10. Dang. The derivative of a constant is, no talk, 4.
0.
Plus 10. Number 9. So you do it.
Oh,
You
I'm
can
getting
do
there.
it.
I'm getting there. Okay.
You can do it unsimplified.
Cosine x minus x sine x plus
Oh,
x sine x.
that's right. You were right the first time. Yeah, it should be minus, right? Yeah. Teacher wrong. So the derivative of the first would be 1 times the second, right, would be cosine of x, plus the first would be x times the derivative of the second, and cosine differentiates to opposite sine of x. Nice job, Sid, plus 20. Good job, absolutely. Nice job. And
Yeah, I can't do this in my head.
doesn't have to be fully simplified. Number 2.
E
Swing
to
loves you.
the x times 6x minus e to the, e to the x, 3x squared, all over 3x squared.
Almost. I think your top row should be flipped.
Okay.
So derivative of the first times the bottom as is, and then minus the first times the derivative of the bottom all over. Good. And then the 3x squared is that. Nice job, you guys. Way to go. And I think that completes it. Good job. Way to go. Count them up. And the big winner, obviously, you're all winners. Okay? But the big point value winner leader is who? Everybody keep track of the points, or you didn't?
It is me. Yeah, I got it.
I think that's it. Awesome, way to go. That's great. That's great. Okay, so what do we have for the winner? Well, gosh, wouldn't it be sweet if we had?
Stop.
You're welcome. Guys, it's a very short discussion today. We know you have your quiz looming, and I know you guys are going to rock star out to the top. Let's just go ahead and remember how we can deal with tangents versus normals, and then you're going to go ahead and take the quiz. Marissa?
Is the quiz like all the ones on here or all the ones that we had to write out for? You know what I mean?
Yeah, it's like 12.
Okay.
The ones you have to write.
You just get it.
Oh.
I mean, they're the same.
Okay.
Okay, ready? Let's go ahead and see how we can apply some derivatives then to tangent line situations and slope problems. So what values of x, if any, does the curve have horizontal tangents? And we saw this last class, and so this should be just a nice refresher to get your juices flowing on a Monday. I know that horizontal tangent means then what's true, right? What's true about my derivative? Vivian?
I'm sorry, can you repeat that?
Yeah, if I have a horizontal tangent, then what is that telling me about my derivative?
The derivative is 0.
Right, and so our plan of attack that you guys formulated successfully last Thursday was to take our first derivative and set it equal to 0. So we just need y prime. This is supposed to be root 3 times x, and so that x is not inside, it's just a multiplier. So that's supposed to cut off, but I was using the math type as part of the smart tools and not the equation editor, and so we'll see how it goes. But this is supposed to be root 3, the derivative of, and then plus, and we just saw how cosine differentiates the opposite of sine, so that should be minus 2 sine of x. So the key for horizontal tangents is that my slope of the original curve is 0. Therefore, if I set y prime, my expression that represents the slope of y anywhere along it equal to 0 and solve for x, I'll find the x values of concern where the curve has horizontal tangents. So we can solve that fairly easily. It looks to me like negative 2 sine of x equals negative root 3. Dividing, I get sine of x equals root 3 over 2, and isn't that nice? We know that happens a lot of places, doesn't it? We don't have a restriction? Well, sine of x is equal to root 3 over 2 at pi over 3 and 2 pi over 3 and forever ever after. So we could write this generalized in two different ways. We could say that x equals pi over 3 plus or minus 2 pi n, and x equals 2 pi over 3 plus or minus 2 pi n for integer n forever and ever in both directions. Okay, and that's fine or whatever, but I want to do a quick verification. So again, I'll go ahead and check by clearing out my original, and we'll do a quick check visually. So second square root of 3, get out of that radical, x plus 2 cosine of x. And I'm just going to go ahead and graph my original. That doesn't look like 2 pi n forever. Yeah?
This is radians, right?
Yeah, this is radians. So what's going on here? Well, can we draw at pi over 3 and see what happens? Let's second draw tangent at pi over 3. And this should be, oh, there we go. So I agree that that's, yes, tangent. What about our 2 pi over 3? Oh. Oh, does that look horizontal? So we do. So what's going on here? Are there more? Yeah? No? So when we solve this, we wanted to know when sine of x was equal to root 3 over 2, and yet my generalized solution plus 2 pi n in both directions would be lots of values, an infinite number of values. And as I look at this picture, I'm only seeing 2 places. I mean, have you guys seen any other places? So what's going on here? Did you guys try zooming out?
Yeah,
And?
nothing.
So what's going on? Ah. So we just had our window for Z trig, for zoom trig, to get us a nice little standard viewing window there. Around negative 2.5. Look at, there's another one. There's another one. So if we went ahead and did second draw 5, and this time I'm going to do pi over 3. Let's go a full circle around, plus another 2 pi. So pi over 3 plus another 6 pi over 3, right? Would that be 7 pi over 3? So I'm going to go ahead and try that. 7 pi over 3. Pinch of salt over the shoulder, and voila! Horizontal tangent. Gosh, that is so cool. All right, but that's not all. Let's go ahead and take a look at something different from Thursday, and that is the application of a normal line. Recall, normal is just calc speak for perpendicular back from geometry. So a normal line, also called orthogonal, right? Orthogonal is another fancy word for perpendicular. Let's find the equation of the tangent line and normal line to the curve at the given x value. And so again, this is just meant to be a quick refresher. You're going to have a chance to apply these problems during your OTL number 2, if I want to be able to get you going on your quiz. So let's go ahead and do our first derivative. Y prime opposite of sine of x. Our x value and y value, the point of tangency. Our x coordinate given, 5 pi over 6. Our y coordinate then would be our original evaluated at. So cosine of 5 pi over 6 is negative root 3 over 2. Is that right? So if I wanted to get my slope of the tangent line, I'll evaluate my y-prime expression at my x value of concern. The opposite of sine of 5 pi over 6 is not positive 1/2, but negative 1/2. Is it negative 1/2? Awesome. So we'll do two problems, tangent line and normal line. Tangent line will be y minus negative root 3 over 2 equals negative 1/2 times quantity x minus 5 pi over 6. Normal line will be y minus negative root 3 over 2 equals question mark x minus 5 pi over 6. So how are the normal line and the tangent line related? How are the normal line and the tangent line related? Sophia?
The slopes are opposite. The reciprocal, the opposite reciprocal.
Absolutely. So we flip it and change the sign. So the opposite reciprocal of negative 1/2 would be what? Positive 2? Yeah! All right. We're going to go ahead and do a quick check then. In each case, I'm going to subtract over root 3 over 2 and check on my grapher. And so I've got y equals clear, zoom 6, and my original cosine of x, and my tangent lines, nope, my tangent line, so y equals negative 1/2. And again, I'm going to leave this in parentheses here, so I don't mess anything up. X minus 5 pi over 6, close, and then I'm going to subtract over that root 3 over 2, right? Because that would be positive, so I'm going to subtract over root 3 over 2. How do we do? Riley, you're in charge here. You're up here, so that's positive 2 for the normal. I can't wait to zoom square here so we get a nice viewing window, but x minus 5 pi over 6 again, close, and then plus, so minus again. How do we go? Did we get them all? Did we get them all? Too many. Is that good? You guys ready? All right, let's go ahead and, where are we? Pi pi over 6? I can zoom trig again. So 5 pi over 6 should be right around here. Here comes for the tangent. And here comes for the normal. So it should be what? Orthogonal side? Uh-oh. That doesn't look very... What do we do? Did we mess up? This doesn't look very good at all. Let's try this. Z5, huh? The square option. Let's see if that is a little bit better. Did I not do Z5? I gotta hit it. And we're waiting, It's grinding. Zoom 5? Isn't that sweet? Because it then it corrects the fact that I'm dealing with a rectangular window here. Come on now. Don't be shy. Come out and play. We're nice. Oh, look at that. That looks perpendicular geometry style, doesn't it? That's pretty sweet, and that's PDFable, baby. You guys are going to have a chance to practice with the slope type questions. So we've got all kinds of things from where the slope is a given value, right? Whether that's horizontal or otherwise specified, where it's parallel to a different curve, so you have to set it equal to whatever the slope of the other curve is, to tangents and normals. It should be, right? It should be a nice little practice, and then we'll set up for some more applications, including particle motion and implicit differentiation next time. But I know you guys are anxious to get along in your quiz, and so your OTL is here. Did it fit on the sheet or no? It did not. So let's everybody take a minute and jot this down because it's not on the sheet because I ran out of slides and I didn't want to have to go to a staple. And I can write it down over there. I'll go ahead and stop the recording and save that to our Moodle site.